Hi everyone, welcome back for another heat and mass video. Today's video is going to be pretty hefty because we have a probably our most complicated example when it comes to heat transfer and mass transfer working together. So the last video that I did, that was a smaller example with the evaporative cooling and the saturation through the pipe, adiabatic saturation. So those were two smaller examples about how heat and mass transfer work together and counteract each other, so they exchange energy from between air that is warmer and water that is cooler, or vice versa, where they exchange that heat and also exchange that mass with each other. So today's example is going to be more complicated because we're talking about a cooling tower. So, if you haven't heard of a cooling tower before, this is a very important principle in chemical engineering. This is what a lot of chemical engineers will work on. And it's essentially heat and mass exchange between water and air once again. And we're using the air to cool down the water so that the water can be used for something. And so the heat from the water will transfer, sorry, no, the heat from the air will transfer into the water to cool it down, and then the water will transfer mass into the air. And that's where that heat and mass transfer are happening simultaneously. And so we're going to be specifically looking at how the water is going to change throughout our cooling tower, how the water temperature, sorry, I don't know if I said that, the air temperature, how that's going to change, and then also how the concentration of water is going to change through the cooling tower too, because we do have that mass transfer and then also the heat transfers through the temperature. And then secondly, we are going to do another Excel where we can see kind of bit by bit how those temperatures and the concentration are changing when we have initial conditions and specific parameters instead of just the theory behind it, which is what we're going to do in the first part. So I have my paper here. So this is completely blank, just has our agenda up there. So I'm going to start by drawing our cooling tower. I'm just going to draw it as a square because it's just a lot easier to think of it that way. Most cooling towers actually have some sort of specific geometry, but for the sake of this video and just understanding the basics of it, we're going to simplify it to a square. And so at the top here of our square, we're going to have some sort of flow in of water. So we'll have the temperature of our water coming in. And once again, this is a cooling tower, so our temperature of the water is going to be pretty hot. It's going to be a warm temperature initially, and then when it comes out the bottom and exits, it's going to be temperature of our water coming out, and that's going to be cooler because we are trying to get the temperature to be lower than what it starts, because this is a cooling tower. And then to counteract this, we're going to have some sort of temperature of air flowing in from the bottom instead. So that's going to be temperature of air in. And this air is going to be flowing up. Meanwhile, the water is going to be flowing down. So they're already counteracting each other when it comes to actual flow. And so we have the temperature of our air coming out at the top, and that is going to be a cooler temperature at the top because the air, sorry, that's going to be a hotter temperature at the top, sorry, because the water is going to give some of its heat energy to the air and heat the air up, and the air is going to give some of its cool temperature, cool heat energy to the water to cool it down. But with this, there also has to be some sort of mass exchange too. So the water is going to be diffusing into the air and kind of change the humidity of the air too. So, excuse me, when our air is exiting, it's going to be more humid than when it enters. And then also, we're going to denote that going upwards is the positive z direction, just because that's kind of our intuition. That's what we're used to. So when we talk about the flow of the water, it's going to be in the negative direction because it's going from up to down. So it'll be inherently negative, and the air will be inherently positive just due to how we've denoted our positive z direction. And we're also going to have some sort of change in z for the length of our cooling tower here. So just seeing how this height is going to change. And this is how I've drawn my arrows here, the water coming in, water out, air in, air out, and they're counteracting each other. And then we also have, I'm going to write on the side really quick here the 3 things that we're looking for. So like I mentioned at the beginning of the video, we're trying to see how the temperature of the water changes. So dTW with respect to position, so over dz, and then dt air, because we're also trying to see the change in temperature of the air, and then finally the change in concentration, so dc over dz. So change in concentration, that's going to be of the water in the air, but I'm just going to write it as concentration of the air. But that's saying how the concentration of the water within the air is changing. So that kind of takes both components there and adds them together. And then within our cooling tower, we have some sort of specific geometry in order to have the best output possible for changing the temperature of the water. So the main point of our cooling tower is to change the temperature of the water as best as we can. And in order to do that, a lot of cooling towers will have a certain packing geometry in there. So that just means that they have some like twists and turns, whatever, that the water and the air have to flow through in order to maximize heat and mass exchange, or mainly heat exchange. So we're going to say that A is going to be equal to our packing component, and the packing component is going to have the cross-sectional area of our tower. So just the area, if you slice it in half and look at what that area is of the packing, that's what that is. And then the volume of our cooling tower in its totality. So we're going to get a meter squared over meter cubed. Oh wait, I think I did that wrong. It's meter cubed over meter squared, sorry, because the unit that we'll get is just meter. So we'll have the volume over the surface area instead, and this is going to be our packing component. And this is just something that we have to consider because that is realistic to real design of a cooling tower. So I've just written this here, the 3 things that we're looking for: change in temperature of water, change in temperature of air, change in concentration of water in the air, and then this is our packing component where we know that it's going to have units of meters. And so in order to look at this a little bit easier way, we're just going to take a little sliver of this cooling tower so that we can break it up into components. So for a lot of our examples, we'll kind of break it into little tiny pieces and then add them all together, essentially like an integral. So that's what we're going to do here. We're going to have some sort of dz length here for each of these little pieces added all together. We still have our same arrows of the air going out and in and the water going out and in. So I'm just rewriting that here. And instead of drawing the packing area as being those crosses like I drew before, that was just kind of a simple way to show that there's something going on within that cooling tower. Now I'm going to draw them as little circles in here because that's a little more likely to what this packing geometry is going to look like. So we have our little sliver here that we're looking at with the temperature and everything still, those flows still going in the same direction as before. And then our packing is going to be those circles, and the length of this little sliver is going to be denoted as dz. So I actually did get the packing component correct the first time around. So it actually is the area over the volume, so it's going to be meter squared over meter cubed. So that area or that unit is actually 1/meter. So I apologize about that. It was actually area over the volume. So it's 1/1 meter instead of 1 meter for that unit there. So looking at this little sliver, we're actually also going to have to consider some sort of volumetric flow rate. So not only does the temperature of the water and the temperature of the air, plus the concentration of the water in the air matter, but we also have to consider that packing component for one, and then also the volumetric flow rate, so how the water is flowing, how quickly, per what unit area, and then same thing for our air. But for the air, it's also going to consider the packing. So we'll start with the water. We're going to denote this as L is going to be our flow rate. It's going to be in terms of kilograms per meter squared per second. So this is going to be our flow rate of water. I'm just going to write an arrow going up there. So this is showing how many kilograms of water are going to flow through per second per that area unit. And then for our air, we're going to have something called our superficial velocity. And I'm going to denote this velocity as being capital G. And this will be, excuse me. This will be our volume meter cubed per meter squared per second. So this is considering our packing component, but this time it's going to be inverted where the packing component, it'll be some sort of flow rate that we have depending on the packing component per a second unit. So it's going to be the volume of our total cooling tower divided by that cross-sectional area times the second component. And this is our, once again, our superficial velocity. So when we are looking at our water, there's going to be three different things factoring in here to solve for our change in temperature of the water in terms of position. So we're starting to make our equations, derive our equations for the three unknowns that we want to find, which once again at the beginning of the video I denoted as the change in temperature of the water due to change in position, and then the temperature of the air with regards to change in position, and then lastly the change in concentration of water in the air, once again due to a change in position. So we're going to start with our dTW dz and begin deriving this equation. So there's going to be three different components that are going to change our temperature of our water. The first two, like I mentioned before, are those heat and mass exchanges. So there's going to be some sort of heat exchange between the water and the air, as well as a mass exchange between the water and the air. But there is a third component that is going to involve our flow rate. So this is going to be our change in thermal energy. And this will incorporate our flow rate here. And we're actually going to say that our change in thermal energy is going to be equal to the change in our mass and heat exchange. So change in thermal energy, that's going to be equal to the flow rate of our water, so capital L, times the heat capacity of water, and then times, this is our change in thermal E. So times our area, that's going to be our cross-sectional area again, times the change in temperature of our water. And then, like I said, this is our change in thermal energy, so this is going to be our left side of the equation here. And then once again, this will be equal to our thermal energy, or sorry, our heat exchange, and then our mass exchange added together. So for our heat exchange, we're going to have to incorporate our packing component. So we'll do our lowercase a, and then that's going to be multiplied by our uppercase A to kind of encompass our total volume that we're looking at, and our sliver is going to be including the packing component as well as the cross-sectional area. And then we have to add our H, which is, as we recall, our conductive heat coefficient, so H. And then we're going to look at our change in temperature, so that'll be temperature of the water minus temperature of the air. And then added to that, so this is our total heat exchange component here that we have. And then for our mass exchange, we're going to also include the packing and the cross-sectional area, so lowercase a, capital A. And then we have our Kc, which is our mass exchange coefficient, similar to that of H for our heat exchange coefficient. And then we're looking at the concentration of water, so that's going to be when water is fully saturated, minus the concentration of the water in the air, which I'm going to denote as concentration of air, like I did above. So I'm going to say that the CW, so I've written it as CW, that's going to be fully saturated water. And that's what that's going to denote. And then if you recall from our last video, in order to relate the mass and the heat exchange and make sure they're in the same units, we have to add that enthalpy of vaporization at the front there. So this is our mass exchange here. We have the enthalpy of vaporization, lowercase a, capital A, that packing and area, and then our mass exchange coefficient, and then our concentration change. So, and then I forgot to add here, these are due to our change in, these also relate to our change in position. So we have our dz here at the end of both the heat and the mass exchange. But when we're talking about our fully saturated water, so CW, that's going to be equal to the pressure of our saturated water, so PSAT, over RT, because we can recall that concentration is equal to pressure over gas constant times temperature, and since the CW is our fully saturated water, we can find this through Anton's equation here, and that'll just simplify our equation a little bit more when we take this to the Excel sheet. So I've just written this here, that CW is equal to, or saturated pressure over RT. So now we will rearrange this equation so that we can get dTW over dZ equals whatever else. So we just have to rearrange a little bit. We got to divide by dZ from both sides, and then divide by our flow rate of water, heat capacity of water, and area. And then we're also going to plug in the concentration of water that we just denoted, that you can solve through Antoine's equation, and back in there too. So if we do all of this rearranging, we're going to get dTW over dZ is going to equal, so we'll have our packing area, the big area will cancel out the big A, and then we have H over, and then TW minus T air. Our dZ has been divided out to the other side, so we don't need that. And then plus our enthalpy of vaporization, our packing A, again, the big A gets canceled, then we have our mass transfer coefficient, and then plugging in for CW, we're going to do P saturation over RT minus concentration of the water in the air, and then once again dZ is taken out. And then we're dividing all of this by our water flow rate, capital L, and then the heat capacity of water. And I'm just going to put here that this is the heat capacity of water, just so we don't get anything mixed up. And then, yeah, once again, that big A will cancel out. So we'll end up getting this equation for d2w over dz, and that just comes from this big equation where we just simplified it a little bit, and then plugged in this relationship here. So now we're going to begin deriving the equation for the change in concentration of water in the air over change in position. And so this time is going to be a little bit different. We do have this change in concentration drive through our superficial velocity, similarly to the change in thermal energy with the flow rate of the water. But this time that's going to just be equal to our mass exchange because there's no heat exchange relating to concentration. So we will have our big G, which is that superficial velocity, times our total concentration. Sorry, that's not correct. Times, it'll be big G times our area, sorry. Big G times our area. And neither of those things are going to change. We're going to assume that this is a steady state problem, so the velocity will not be changing, and then obviously the area will not be changing because this is a rigid body. And then we're going to be looking at the change in the concentration of the water vapor in the air. And once again, saying C air is saying the concentration of the water within the air. And when we're talking about CW, that's going to be our fully saturated state with fully saturated water. And then that's going to be equal to, like I said, just our mass component. So now we have, once again, our little a, our packing, times big A, times Kc, the mass component. And then we're doing concentration of water again, minus concentration of air, times dz, and then once again times the enthalpy of vaporization. Actually, that is not in there this time. So this is what we have for concentration of air, so that's the concentration of water in the air. Now we're going to rearrange this so that we get this on one side, and then we'll just divide over the G and the A. So we'll get dc air over dz equals, the A's will cancel out, so we'll have our packing over our superficial volume times the mass coefficient, and then plugging in that relationship for CW, we have Psat over RT minus C air. So here is that expression that we have now for the concentration of air due to change in position. This is what we have, but we are going to add another substitution in here in order for these equations to be as simplified as possible. If you'll recall from our last video, we had derived a relationship between the heat diffusion coefficient H and the mass diffusing coefficient Kc. So that relationship was, I'm going to go ahead and go to the other page. H equals Kc times rho Cp. So that is saying that the heat diffusing coefficient is equal to our mass diffusion coefficient times the density and the heat capacity of whatever we're looking at. So we are going to plug this relationship in for Kc. So we're going to solve in terms of Kc really quick, and that'll just be H over rho Cp. And that's what we have right here. And we're going to plug in for Kc this relationship so that we limit this down to only having H in there instead of both H and Kc. So for our change in concentration of air over change in position relationship, we'll have that equal our A over G, and then this is times, instead of Kc, we're going to put H over rho Cp. And this heat capacity is going to be the heat capacity of air because we're looking at the change in concentration of water vapor in the air. So this is going to be heat capacity of air, and then times our Psat RT minus C air. And then the same thing, we're going to plug this relationship into our first equation that we derived of the change in temperature of the water is going to equal, and then we have AH TW minus T air over L heat capacity of water plus, and then we have the enthalpy of vaporization, A, and then instead of Kc, we're going to plug in, once again, H over rho Cp, and this is heat capacity of water this time because we're looking at water here, times Psat over RT minus concentration of vapor in the air, and then once again this is also divided by LCP of water. So when we plug in this relationship for Kc, this is what we get, a simplified version of these two equations that we already derived. And then lastly, we just have to solve for our change in temperature of the air. That is the last unknown equation that we need to find. Lastly, we are going to look at how the change in temperature of the air is affected due to position. So this is going to be our most complicated equation because this temperature of the air is once again including both concentration and temperature because the concentration of the water in the air is affected with the air, but for the water there's no concentration component necessarily. So the temperature of the air is going to have both temperature and concentration, and then that's going to equal our heat and mass exchange once again. So we're going to have that the density of air times the area times g, which is that superficial velocity, is all going to be multiplied by a big piece that is going to be changing. So we're going to have to do derivative of this big piece, and that's going to be the heat capacity of air, because we're talking about air here, times the temperature of the air, plus the enthalpy of vaporization divided by the density, again, times the total concentration of water vapor in the air. And so this big section here is all taken the derivative of, so that's what this side looks like. And then once again, this is going to be equal to our heat and mass transfers still. So we'll do heat first. We're going to have our little a times big A times H, temperature of the water minus temperature of the air once again. And then added to our mass transfer, which will be enthalpy of vaporization, little a, big A, mass transfer coefficient Kc, and then times concentration of water minus concentration of air. And then these have dz next to them too. Almost forgot. So then we have our traditional heat and mass transfers there too. And then we can plug in for Cw again and divide over the rho Ag. So before we begin to plug in these things, so concentration of water, and then we could also plug in our Kc, similarly to what we did in the other two equations, we actually don't need to do that because this last piece right here is redundant to the change in concentration of air equation that we derived because they are essentially the same thing. So we don't have to account for it here again because we've already accounted for it in that equation. So we can actually cancel out that last piece there. And then if we simplify to be the change in temperature of the air over dz, we end up getting our pack A value, our heat transfer coefficient, TW minus T air, all over the density times the superficial velocity times the heat capacity of air. And so this equation ends up simplifying a lot nicer than you might think. So that last equation is redundant to this one, so we don't need it. And then we can just simplify here, get change in temperature of the air over change in position equals this expression here. So that actually simplifies a lot nicer than you might think. So we now have all three equations here. We have the change in temperature for both the water and the air and the change in concentration. So those are our three big equations here that we were looking for. Okay, so welcome to the second half of the video where we take this into Excel using initial conditions that were given. So at this top part here, these are all known values. So these three here are from Antoine's equation. So if you recall, Antoine's equation is how you solve for the saturation pressure. And this is specifically the values for the saturation pressure of air. And then we also have our gas constant R here. And then dz, which is just going to be our counter. So that's like those little slivers that I talked about before. And then these are two conditions that we are given for the specific example. We know what the temperature of the air is coming into our cooling tower and of the air and of the water. And then we know that for one example, we're looking at the relative humidity of the air being 0.1 when it goes in, and then the volumetric flow rate is going to be 10 kilograms per meter squared per second, and then oh my gosh, I'm forgetting the term. Superficial velocity is going to be 5 meters per second, and then I'm forgetting what this is called too. I have the notes right here, so that's what I'm looking at. The packing component, A, is going to be 100, and then we know that H is going to be 50. That's our thermal diffusive coefficient, and then we have these two values just can be looked up. They're heat capacities of water and air, and then lambda can also be looked up because that's the enthalpy of vaporization. So you'll notice there's a couple values here that we're missing. So these are values that we can actually calculate. So we're going to begin by calculating our saturation pressure of air, actually. So Psat of air. And I'm just going to put this over here. Once again, this is solved by using Antoine's equation. So we're going to do 10 to the, and then you'll recall it's A. Pretty sure A minus, and then B divided by C, no, I think it's A plus, actually. A plus. And then this is C, no, wait. Let me try this and see if this works. I'm pretty sure, let me write it down. So Psat equal to A. Yeah, I think it's minus. And then plus, and then we're looking at the temperature of the air coming in, so here, but then we have to subtract 273 because Antoine's equation is these coefficients are given in terms of degrees Celsius equaling millimeters per mercury, so we have to subtract 273 to get this in degrees Celsius. So we have this here, and we'll get our value, but then we have to change this into pascals. So we'll do 101,325 divided by 760. And that is just the that's just the factor that you have to multiply by in order to change it from millimeters of mercury to pascals. Okay, this does not look right. So I think I put the wrong equation in here. Let me try. Okay, that does not look any better. Give me 1 second. Okay, so I'm realizing what I did wrong. We're not actually plugging T air in here, so we want to plug in just a value for the saturation of air. So when it's at its maximum, so we're going to say 100 degrees Celsius here. So this is more correct answer here. So that is my fault, because later on we're going to be plugging in the actual T air in instead. But for here, we just want the Psat of air when it's like at its max, so that's going to be 100 degrees. So we'll multiply this by our coefficient here and just get that number over here. So we can create a formula here. Okay. Okay, sorry about that. And then next we're gonna solve for our density of the air. So this will be equal to the molecular weight of water, or the molecular weight of air, which is 0.029, and then times 101,325. So that is just the standard pressure, and then divided by our R times T air in. So that's going to be our density here, and then from here we can solve for our mass diffusion coefficient. And so in our equations over here we had solved by plugging that in, but just to make it a little more simpler for actually plugging into the Excel, we're going to go ahead and solve for this over here using that equation. So if you recall, that's going to be H divided by the rho air times the heat capacity of air. And so that will be our value for Kc, which is related to our Lewis relationship again. That's how we get that equation. And then we're just putting that in here so that it's easier to type in all the values later. And then we have to solve for Csat. So that's the concentration of the saturated air. So that's essentially saying when the air is saturated coming in, what is that concentration? And that will be equal to our Antoine's equation again, but this time we're going to be solving actually for the temperature of the air coming in. So it'll be A minus B divided by C plus temperature in, and then we have to subtract from 273 this time because that is in degrees Kelvin. And then in order to get this in correct units, we have to use that converting factor, 101,325 divided by 760. And then all of this will be divided by, let me put this in big parentheses. All of this will be divided by R times the temperature of the air coming in again. All right, so now we have the concentration of the saturated air coming in, and then, sorry, the saturated air, and then the concentration of the air coming in is going to be equal to that Csat times the relative humidity. So this here is saying what the humidity of this is when, or sorry, what the concentration of water in the air is when it's fully saturated, which means that the relative humidity is 100%, and this is what it is coming in because we know that the relative humidity coming in is 0.1, And so 0.1 of 100% humidity, that's what the concentration will get coming in is. Um, okay, perfect. And then for TW out, this is our other number that we don't know. And for the other Excels that we've done, we've had to use solver a couple times, and this is the value that we're going to have to use solver on. So this will have to be a guess for right now. So we're just going to guess that this is equal to 303, because that is the temperature of the air coming in. So we're just guessing that it's the same as the temperature of the water coming out. And this is Kelvin, but this is our guess value, just to keep track of that before we actually change that using solver. So once again, similarly to what we've done in other Excels, we have to do some sort of counter here. So we're gonna have this fill down to 1,000. So stop value is gonna be 1,000 here. And then the position that we're at will just be this times our DZ. Okay, I don't know why this is doing that. Times DZ will be B5. Okay, and then we'll fill this down such that our final length of the column is going to be 5 meters long. So that's what we want here. And then the values that we're actually solving for, once again, are going to be the concentration of the water within the air, the temperature of the water, and the temperature of the air. So then here we'll begin to plug in those equations that we had solved for in the first part of this video. We also have to add the changes in saturation, so pressure saturation of the water. And then to make it a little bit easier as we're going through these equations, I'm just going to put over here the difference in our concentrations, because you'll have noticed that in those equations that we derived in the first part of this video, there's a lot of areas where we're going to have the concentration of the water minus the concentration of the air. So it just makes it a little bit easier to make a whole column for that. And then we're going to have our dTW, dt air, and then dc air. Okay. And then we know that the concentration of our air, so this position right here is going to be the very bottom of our tower, which we'll recall that's when the concentration of the air coming in, so that'll be equal to this value here. And then at the very bottom, that's going to be equal to our temperature coming out, because at the bottom of our column, we have the air coming up and down. So that'll be temperature of the water coming out. Temperature of the air at the bottom is air in. And then for PSAT, this is going to be the pressure, saturation pressure of our water. So of the water within the air, sorry. So we're going to do Antoine's equation one more time. So 10 to the A minus B divided by C plus, and then we're doing the temperature of the water. So that'll be this here. And then minus 273, because this is in Kelvin. And then we need to multiply this by our factor again to get it into pascals. 60. All right, and so this will be the saturation pressure of the water at this associated temperature. And then once again, our concentration difference is going to be that concentration of the water minus the concentration of the air. And in order to get concentration, that is equal to pressure over gas constant and temperature. So this is concentration of the water, so we're going to do this PSAT divided by R times the temperature of the water. And then this will be minus the concentration of the air. So that's going to be our value here. And yes, so now we're going to start with typing in our equations that we derived for change in the temperature of the water first. So this is going to be equal to, we have our A times H. I guess I need to put this in parentheses. A times, oh, sorry, this is the wrong thing. Yes. I hate Excel. Times H times the change in temperature, so that will be temperature of the water minus temperature of the air. Okay, nope. And then we'll do that. We'll close out that parentheses, and then this will be divided by L times the heat capacity of water. And then this will be added to our enthalpy of vaporization here times A times H. And then this will be divided by the rho of air, or density of air, times the heat capacity of air. And that's this part here, and then, so, yes, and then times the concentration difference, and then this entire thing is going to be divided by L times heat capacity of water again. Okay, and so this is our change in the temperature of the water so far, and then for change in temperature of the air, we can look at this and say this is going to be equal to A times H times the temperature of the water minus the temperature of the air divided by rho air times G times Cp, heat capacity of the air. There's that value here, which makes sense because we have that temperature difference right now not being equal to anything, and then concentration of the air is our last equation here. And this is going to be equal to, go ahead and flip back to the old equation when we didn't have a substitution. That's going to be equal to A divided by G times, and then we're going to have Kc, which we calculated here, times the concentration difference. And that's what we get for the concentration of air. So perfect. Now that we have those initial ones plugged in, so now we're going to do what we always do, which is take where we are plus current position times that differential for each of these, where we are plus current position times differential for each of these values. T air. Okay, and then we can pull all of these values down. Did that slowly but surely. Okay, perfect. And then now we can send this all the way down. All right, so this is showing how all of these values are changing as we're going higher and higher up the cooling tower. And yeah, you'll see these are some really funky numbers. So this is not the kind of numbers that we want to be getting here. So you'll see it gets really, really weird around here. And so these numbers are pretty funky and not what we want. Let me double check something really quick to see if I maybe typed this in incorrectly. Let me try changing this to our DZ value and see if that makes a difference. Okay, it does slightly, so I'm going to go ahead and change this out to our DZ instead of that. All right. So even still, we're going to start to get funky values somewhere around here. These values start to look really big, really intense. Like this one right here, this is like super, super big. So let me see what this is. Oh, sorry, we don't care about that one. The temperature of the water is what we really want to focus on, because we know that the temperature of the water is supposed to be a certain value at the end here. It's supposed to equal 50 degrees Kelvin plus 273. So it's actually pretty close right now, but it's not quite right. And we want to make sure that this is the correct value. And you'll recall that we made a guess for what the temperature of the water was going out. But we know what the temperature of the water is going in. And this is where the water will be going in because, once again, it feeds in from the top. So we need to do solver again in order to get this to be the correct value. So this is going to be our H1003 value. So due to this temperature of the water coming out guesstimate, this is what the temperature of the water coming in is associated to be, but we actually want it to be 323. So it's pretty close already, but we still have to do the squared difference and then solver in order to get it to be actually correct. So we will do the sum squared value of what we actually want, which is this 323, or here, same thing, and then what we actually got, and then square this value, and we're going to use solver in order to minimize this value. So this value we want to minimize, and we're going to change what the temperature going out is. So we can solve. Perfect. So we know that the temperature going out actually needs to be 303.08, which is once again very similar to what we had put in as the guess. So we did pretty good with the guess, all things considered. So the temperature of the water going out is actually 303.08 Kelvin instead of 303. And that, double checking that, we're just making sure that we have our water coming in at 323, and that's what we have. So that is perfect. Okay, so this was looking at a relative humidity of 0.1 coming in, and typically with cooling towers, it's better to have the concentration of water in your air when it's coming in to be as low as possible. So we're just going to take a peek at what it looks like when you have a relative humidity of 0.5 instead. So this is going to change our numbers a bit. So we'll see that this temperature has changed a pretty decent amount. So this is where our water is coming in. That is now at a different value. And then at the end here, this is still the same because that's what we've calculated as the temperature of the water coming out. But the temperature of the water coming in is significantly colder than what it could be. So that's kind of saying that when the humidity of the air is higher, the efficiency of the cooling tower is lower. So it's saying that the temperature of the water, it's not as hot, but it's still cooled down to the same temperature, versus when the relative humidity is lower, the water can be hotter and be cooled down to that temperature. So we'll do solver again. Just see what we can get here for the temperature of the water coming out if the water coming in is 323 again. So that has changed a little bit. It's raised a couple of degrees here, so it's 305 now instead of 303. So that's just goes to show that more humidity in the air when it's coming in makes the cooling tower less efficient. And then another thing that you can change is also the height of our tower here. So this is going to change our values once again, because now we only have a tower with a height of 2.5 rather than 5, so that cut it in half, and so now that's changed this value drastically too, once again. And that makes the tower less efficient too, because the temperature of the water, coming in, well, actually, that makes it more efficient because the temperature of the water coming in can be hotter. No, it's still colder. Sorry, I'm getting messed up. It's still colder. So the temperature of the water coming in is colder, and it only gets cooled down by 10 Kelvin. Whereas before, it could be 323 with a taller tower and get cooled to that temperature. So having a shorter length of your tower also changes efficiency to be worse. So we could do solver again. See what we get here. Perfect. So yeah, once again, that's showing that if our temperature is 323 coming in, then the temperature out is 308 instead of 303. So it shows that this cooling tower is less efficient when it's shorter. So then, yeah. So that's kind of showing everything that I wanted to show today with this video. So we derived all of these equations here for change in temperature of the water, air, and the concentration of the water within the air. And we've modeled it on Excel to kind of show how these numbers are changing as you go through this cooling tower, and also showed the effect of changing the length of the tower, as well as how that temperature is changing when we guessed it versus what it actually is. And so yeah, that is everything for the video today. Hope you enjoyed.